this session is going to be slightly at some level what I believe is slightly a lighter session, but more conceptual than very technical, right. So this all throughout the school you were you were looking very closely at game theory and getting into the details. Now we are going to slightly pan out and take a bird's eye view of how so we are currently quote unquote in the era where people are thinking that artificial intelligence is like the next electricity, so on and so forth. And then I just thought that okay, this might be a good place to sort of bundle all the how the conceptual thread that connects all the various decision making problems, of which game theory is also something that talks about decisions. So this is the plan, right. So first what we will do is to talk about the decision theoretic framework of artificial intelligence, right, which is slightly different from what we read from, not slightly different, slightly more principled than reading things here and there, and then every day we come up with some so there is some new technology that is driven by AI, and then you read it in the papers, and then you really think that okay, the AI is going to conquer the world and so on and so forth. But then ultimately all these things, at least from the outside, looks very disconnected. My effort here is to connect all of them, and maybe connect some of the topics that you would have heard in various other courses in a single framework, and then just list them down so that you will see the connection. Then we will look at alpha beta pruning, which is AI, but then it has no machine learning, right. So that is also something that we will slightly touch upon, right. Like now that the word AI is become synonymous to machine learning, and machine learning has become synonymous to deep learning, right, and people seem to use these words interchangeably, but then there are some conceptual distinctions. So this is also AI, and so we solved a game like chess with alpha beta pruning, which is AI but no machine learning. Then we will look at upper confidence trees, which is solving AI with reinforcement learning, specifically ideas from multi-arm bandits, which I think Dr. Shweta would have covered. And then AlphaGo, which is basically packing upper confidence trees and deep learning together, right. And then mostly I am going to I mean it's going to be both sometimes more detailed, sometimes more bird's eye view. I am going to mix and match things. Yeah, so I am in general not really great on time management, but let me see how I will do today. Okay, so in general what we see in popular culture is this kind of an idea that when we say that AI is like okay, this is some big machines with a lot of memory, a lot of speed, right, and right, but then intelligence is going to be a little bit more than memory and speed. So what we will do is we will do this little exercise, right. All of us will write our own definition of intelligence, but then I am going to give a prompt in the form of a video, right, so that you can define, right, and then I am just going to get some oral responses. Keep that in, we will keep the responses in mind, and what we will do is we will I will talk about the framework and then put in the details in the framework, and then we will see whether those things connect, right. And so the by the end of this exercise we would understand why the current the decision theoretic framework of AI that I am going to show connects captures all the useful things that we will want about AI, right, and helps us to talk about a lot of things formally in a single place. Okay, so I am always always been fascinated with the animal world. So this is a video that I always ensure that I play in any of my sessions on AI, right. So maybe we can watch it, and then using this as a cue or a prompt or whatnot, right, like a starting point, you can sort of trigger your imagination and write your own definition of AI.
Inside wooden cage, positioned so deep in the narrow box, is out of reach of the crow's beak. But Alex has positioned a number of other objects nearby. The question is, can 007 use the tools available to solve the puzzle?
Imagine that you're a crow. Here's your food in a deep hole. How would you go about, with the tools available to you on this table, solving this problem?
The bird's toolkit includes a short stick hanging on a piece of string, 3 stones inside wooden cages, and a longer stick trapped in a plastic box. First, the crow must use the short stick to get the stones, and then use all 3 stones to get the long stick.
And now the crows can take this and probe it into the hole and roll, much better than I can, the food out of the hole and get themselves a nice tasty reward.
It's a complicated task. The crow is familiar with the individual pieces of the puzzle. He's done each of them separately for a food reward. But this is the first time he's seen them arranged like this. 8 separate stages that must be completed in a particular order if the puzzle is to be solved. If the bird succeeds, it'll be a world first. He takes time to have a look. And then starts with the short stick. He finds it too short to reach the food. He then sets off to get the first stone. Got it. But he doesn't seem to know what to do with it. And another. He appears to be stuck. But now something seems to click. He dispatches the first stone. Then returns to collect the last one. Got it. The final stage. Success. 8 individual stages complete. The crow performed all 8 tasks in the correct order.
But
Yeah.
what's the capture you have video?
Actually, you will be amazed by the kind of intelligent behavior in the animal kingdom, especially with this octopus, right? So they have, they can solve puzzles, they can sort of move around multiple mazes, and yeah. So anyway, so let us take this as a some kind of a hint or whatnot, right? So if I ask you to define intelligence, right? Don't define what happened in the video. The video is just to sort of kindle your thought process. But then if you were to come up with the definition of intelligence, so how will you do it, right? So maybe take a couple of minutes, and then we will hear some of the responses. Note down the key points and then see whether the current framework that we are having captures those, right? Maybe, yeah, I will give you maybe a minute. I mean, any definition is fine, right, as long as it captures one aspect or the other, and once we have all the responses, we will have covered most.
Ability to solve some tasks to get some reward.
Solve. Okay, is this very small? Okay. Okay. What else?
Perception to see
Okay.
8 input. Utilizing the tools in our toolbox, things that we have.
Okay. Okay.
Individual
Rationality. Okay.
learning and adapting.
Learning, adapting. Okay.
Intuition to solve a problem never seen before.
Which one?
Intuition to solve a problem
Okay.
never seen before.
Intuition. Unseen problems. Okay.
Observing and analyzing the surroundings.
Okay. Observing the surrounding. Okay.
Gathering the data.
Okay. Okay. Some more.
Decision making.
Decision. Okay. Decision making. Some more.
Creating new information from abstract current information.
Okay, that's already there. New unseen problem. I have to write this big, is it? I thought I would get away with writing really small on that board. Anyway, let us see. Some more. Reasoning. Okay. So yeah, maybe some of it will be present in the framework that we will look at, or maybe not. You will see. Do you want to put some more things? Awareness of what? Okay, awareness of environment. Okay.
Goal oriented.
Okay, there is some goal. Okay. Okay. So, okay, if there is not much to add, then what we will do is we will see what the experts have to say. So, experts will say that artificial intelligence is the science of common sense. This is some definition, and there is another definition. This is by this Russell and Norvig. This is a very standard textbook on AI, artificial intelligence, a modern approach. If you would have come across these authors. So, they say that AI has to do with smart programs. So, let us go and write some, right. So, I am just going to expand on this theme a bit and then illustrate what do they mean by common sense, science of common sense, and what is the challenge in achieving, or in handling writing smart programs for common sense tasks. Okay. So, and then I will slowly bring in all these things in the, you will see all these things in the setup that we will eventually look at. See, some of the common sense tasks, right, is to say drive cars, or just walking, right, or just conversing with people, or say identifying objects, ability to play games, right. These are things that human beings excel much better than the machines, right. So, if it is something like solving a PDE, or making a complicated calculation, or writing an algorithm, right. So, we already know that computers are better, right. In problem solving, computers are better. These are but common sense tasks which we seem to be much better than computers, and the entire goal of AI is to be able to make computers do these tasks at a level which is comparable to human performance. Okay. So, that is the overall goal of AI. So, if you want me to define what AI itself is, right, which is in a way how AI is, if you want to tell me how AI is separated from machine learning, it is about these tasks. AI is worried about the set of problems, right. Machine learning is one of the methods, and that is what we would eventually see. There are a couple of ways of achieving the same thing, maybe one driven by machine learning, one without machine learning, right. In machine learning, what you do is you actually are data dependent. Okay. So, okay, so that is the point, right. So, the challenges is that, so when you say science of common sense, in science in general, let us say take example of physics. If you want to solve look at the laws of motion, you want to design a vehicle, or if you want to design some let us say an automobile or a spacecraft, you have the laws of motion, and then if you want to achieve motion you have the Newton's laws, but then if you want to achieve common sense, like what is the law, right? There is no law that governs, there is no direct differential equation or something like that that governs a chess, right, or that governs movie recommendation, or that governs natural language. So, this is one challenge. The other challenge is that the smart programs, they have to, as somebody says, they have to learn and adapt, right, and but we know that okay, we already have programs for all these things, we have automated all these tasks which actually really do not require any smartness. So, the reason is that these are things right which can be broken down into some kind of a if then else statement very directly, right. So, in the good old days if people were booking tickets, you just go to the station and then they will have these printed tickets, and whatever is the quota from that station to the destination that you are asking, they will just issue the physical ticket. Later on that process got automated where you still filled the forms, but then it got computerized where there is an data entry operator, and finally what happens is that you just execute this bunch of if then else statements, maybe slightly couple more cases, right. So, ultimately the point is that you can automate these tasks because you know how these are executed as a sequence of commands, okay. But when you are saying that how do I walk, so okay, so when you ask how you walk, the only you can say that okay, right leg forward, left leg forward, right leg forward, left leg forward, right. That is the only sort of command that you can break it down to, but that is not enough. So, you take a robo with legs or whatnot, you cannot go and write a code that says that while I equals 1 to infinity or whatnot, right step forward, left leg forward, the robo is not going to walk, right, which means that we have to somehow program things for those tasks which we know how to do, but we ourselves do not know how to break it as a sequence of commands. We do not know the commands. If you know the command sequence, we can actually code it, right, which is why you need the paradigm of learning from data, right. So, which is why it calls for a different paradigm, okay. So, means basically you have to code things such as speaking, such as identifying objects. If you ask you how would you identify a chair, I mean later on you can rationalize saying that okay, you can give some explanation of how you identified a face or something. You can say that I saw the eyes and then there is a nose, that is all later, right, but that is not how you are actually identifying, you are just doing it, you have learned to do it, right. So, which means you cannot actually code it like if then else statements, because you really do not know what it is, right, and that is where the difficulty is. So, we have to program computers to perform tasks which we cannot specify as commands, okay. So, then the very first challenge is that you do not have explicit laws, or you do not have explicit model, you do not have explicit Garni equations, but then you have data. So, you have lots of data, and then with that data you have to figure out how to come up with the right decision, right. And the second challenge is that if you is what is known as curse of dimensionality, right, which is in a game like Go, or right, or in a game like Go especially, the number of board positions is greater than the number of atoms in the universe, right. So, I can take a very simple example of say I want to make some AI to decide on how to make decisions in this say let us say there is a traffic junction, right. Each lane position it can have 1 to 10 vehicles, right. So, the total number of possible number of vehicle configurations is actually 10 to the power 4, right. If I add one more junction, this becomes 10 to the power 4 into 10 to the power 4, so which is 10 power 8, right. So, that means that as and when you add one more extra variable, the number of combinations just blows up quickly, and then you will not be able to write this many if then else statements. You cannot just say that oh, if this is 2 comma 5 comma 6 comma 1 comma 9 comma 8 comma blah blah blah, make this decision. You cannot write these many if then else statements. So, that means whatever algorithm that you are doing should do something else, not just write if then else statements, okay. But ultimately what we are going to write is a code, it is a program, okay. So, now the question is that okay, before we go to the framework that captures these things, what we can sort of do is to look at I will take this down. So, we can look at some of the state of the art, right, which is something like object classification. This is ImageNet, this has almost 1,000,000 data points with thousands of categories, and each category has 1000 examples, and you have deep learning models which perform really well on this data set, something like 85% to 90%. And then you have something like Google Duplex. I mean, now there is ChatGPT, but then this is ChatGPT is just still text, right. So, this can actually converse in human voice, and then if you have time, just please go and take a look at Sundar Pichai's launch of Google Duplex. Okay. So, where there is a bot that sort of talks to people. I mean, it can book restaurant appointments, it can book a haircut appointment by negotiating with other humans. So, it means that it sort of is able to do this, achieve this. Right. Then we have achieved state of the art. I mean, we have algorithms that can play Go with at human level or even more than human level, and even chess, right. So, the current this alpha chess is perhaps 4000 or 4500 rating. Okay. So, there was a time, so when this happened when I was in DeepMind. So, they were training this, so they had done this Go, then they were training it for chess. So, Demis Hassab is one of the founders. So, he himself is a chess grandmaster. His rating is around, I think, 2500 or something of that sort. So, there was a half an hour window in which it was hovering around that mark. So, he missed couple of meetings, and then the alpha chess sort of trained much ahead of him. So, in the evening it is like, yeah, it is no longer playable by him. So, they wanted to have that match, but then yeah, he missed that meeting, and that was it, right. So, we have achieved these things, but what I would want to impress here is that apart from the success stories, at least an audience like us, we should be able to understand the technical backbone that lies behind these things. It is okay for common public to read it, consume it as some sort of great step, I mean single step for man and huge step for a mankind sort of a thing, right. But the larger thing here is that we should be able to talk about these things in much more formal nature, and that is what I think we will do that exercise in a bit, right. So, these are the successes, and as I say, this is all engineered, right. So, this is all not magic. There are principles, and then you follow the principles and you engineer them. Yeah.
If there is no presence of human being, then how is an artificial intelligence playing chess? How is it learning?
Yeah. So, that is what is known as self play. Okay. So, you have two agents that play against each other. That is something that we will see how that happens. Okay. So, then you can have automated driving is also possible. So, now without much of I mean, since we are hard pressed on time, so what I will do is I will introduce the decision theoretic framework, right, where these are the okay. So, this is the diagram, and then we will try to understand the various parts of the diagram. Then we will see how various tasks can be captured within framework, various decision making problems, and I will sort of list down the various algorithms that you can read in the multiple of the courses that you would have perhaps done before and you will do in the future, right. So, the decision theoretic framework is the following. So, there are two entities, one is the environment, right. So, this environment, right, and as somebody says, so this environment part is there. Then this awareness or observation. So, what the agent does is to sort of observe what are known as these features, right, and then the agent makes a decision, and based on the decision again you have a sort of a reward, right, and again there are these various tasks. Okay. So, we will come to what is this intuition, unseen problem, of course data gathering in a bit. Okay. So, first we will understand the various kinds of tasks that are there. Okay. So, firstly what is the environment? The environment as what is known as the state, which is typically unknown to the agent. What the agent observes are known as the features, right, and the agent makes a decision using what is known as a decision rule. So, the goal is to learn the right decision rule, which is nothing but a map from the feature space to the decision space. Okay. And the goal is to find the optimal decision rule to maximize the rewards. Okay. So, now what are the various kinds of tasks? right. So the tasks you can broadly classify into 3 categories. One is description, the other is prediction and control, right. And what is a described task? And then again control is basically you can prediction again you can classify into static and dynamic. Control again you can split it into single agent and multiple agent. If it is multiple agent, that becomes game theory, right. If it is single agent, it is still single agent control. Again you can do it static, dynamic. So we will now quickly have a look at this sort of classification and then see how everything sits in this nice framework, right. As I cut some of these lines, as I make some changes here and there, I can sort of cover almost everything that was shown in that tree, right. So the first thing is what are known as descriptive tasks, for which we have what is known as
I think I missed it. What was the difference between the prediction and the control?
yeah. So we will come to, so we will come to it. So the very first thing is what is known as the description problem. Okay. So in a description task, so what you are worried about is it's also what we call as unsupervised learning. Okay. So I will just show couple of examples and then we will write the formal thing, right. So what you are given is the agent is given some features, okay, and the agent has to come up with some kind of internal representation. It has no decision to make, right. So the very first task in the decision making thing is a descriptive task where there is no decision to make, right. So I am just going to write a bit of small font, but I hope it is a descriptive task. Okay. So what happens here is that so there is this agent, okay, and the agent is given these features, okay. All these features are some xi, this is your data, right, where the xi's come from some distribution, okay. This is the model. You think that the xi's come from some underlying probability distribution, you are just given these features and that is about it. You can do whatever you want to do with the features, it is up to you, there is no decision to be made, okay. Again what are such tasks? So suppose I give you a set of articles, right, these are all English documents, but then you can always put them in some RD, right. So these are all points in RD, this belong to RD, right. So basically what you can do is you can do a frequency of, you can have a vocabulary and you can sort of count the frequency of words that occurred, right. So each article is a vector in the dimension r to the power number of vocabulary, right, number of words in the vocabulary, and then these are just vectors, right. And what I can do is cluster them, right. So there are these points in RD and then you can cluster, you are not making any decision, right. And you can do what is known as this kind of what is known as this dimensionality reduction. So I have data which is spread in this direction, which is in the original coordinate system, then you can sort of have a rotated coordinate system and then you can see that okay, most of the variation is in this direction and then very less in this direction, and you can sort of choose to ignore this direction. This becomes what is known as principal component analysis, okay. So again I will sort of list down the methods and also so this is the model based method, there is no model based method here, okay. So there is the data driven methods. So the data itself is xi, I equals 1 to n, all of these things belong to RD, and these are what are known as so the data driven methods, which are known as which is nothing but the machine learning method. Here you can just say that clustering, PCA, right, denoising, so on and so forth, okay. Okay. So this is where you would see all of these autoencoders, if you are aware of, etc., right. Okay. I will also say where deep learning plays a role in all these things, okay. So okay, the next task is what is known as the prediction task, where what your where the corresponding machine learning paradigm is it's supposed to be prediction task, the title is incorrect, it is predictive task, So, the very first example is that of static prediction. Okay. So, the paradigm that is for such predictive task is what is known as supervised learning. So, here what happens is that, so there is a true label in the environment, okay, and then the agent observes the features and then it has to predict something, it has to predict the true label, right. So, this predictive task, so what happens is this agent is there, okay. So, there is this environment, okay. So, the environment generates both the features as well as the true label from some joint distribution, okay. And then what happens is that the agent gets to see only the features and then it has to predict y hat, okay. And then it is given a loss which is basically an indicator of y I not equals y hat I, right. If y I is not equals y hat I, you say that there is a loss of 1, if the two of them are equal, then you say there is no loss, right. Suppose if I give you the model, if it give you p x equals p y and p y given x, the model based approach is what is known as Bayesian decision theory, right. And in general the data that is given is the original label and the true label, I mean the features and the label, right. And these are standard methods. This is known as supervised learning. So, these are unsupervised, this is supervised, right. I mean, see any of these things that you will learn, which is linear regression, logistic regression, right, all the deep neural networks, CNNs, right, for say image classification, etc., they go under this bin, right. So, here the decision is a predictive decision, right. As you can see, just data, there is only one arrow mark. Now, you start seeing that the information flows from the environment to the agent and then you start making a predictive decision, right. So, and then you give a feedback which is a loss, right. So, this is the decision that, so it is basically a predictive decision, okay. So, now again you can put some kind of a, this is basically static, you can extend the framework to, I mean I will just flash these examples and then you will see, yeah, okay. So, this is what happens. So, in image classification you just say give a fee, I mean if you show a dog and then it has to predict a dog, if you show a cat it predicts a cat, if you show a tiger and it predicts that it is a cat, then you give a loss of 1, this is how you set it up, right. And in the case of regression problems, what happens is that you predict the label is a real number and then you just give a squared loss or a loss that tells the absolute distance between the true and the predicted label, okay. So, this we have done. So, now here we have now with dynamic prediction. So, what happens in dynamic prediction? So, there is a temporal connection between the labels themselves, right. So, say for instance in speech, okay. So, suppose you have this sentence Betty bought some butter, okay. So, that means, so this is the true state, this is the true label, right. What you are hearing, what you observe as an agent is just the audio, right, the sound waves which are some vectors in RD, and then you have again you have to map it to the word that got spoken, right. And again, so here what happens is that so you have, so in dynamic prediction you have this model. So, the model is very simple. So, here the data model, where is this? Okay. So, in static prediction you say that okay, each label gets generated by some thing and the feature is generated given the label. So, for dynamic prediction you have the same model, all that you say is that the yi plus 1 or yt plus 1 is distributed based on right the past, right, and the xt is just based on, right. So, it is something like this, right, like suppose I say that I want to generate a story, right. So, I start with once, right, this is one word, right, then you would want to say upon, right, either I can go to upon or I can just say there, right. Then when I say upon, it is always a time, right, then I can say there lived, right, then again it can branch to all sorts of things, king, a queen, a girl, a boy, anything, right. So, basically that is how we think language gets generated, right. So, the next word that the speaker speaks is a function of the past, right, and the word that gets uttered is a function of the current word, right, the sound that gets produced, and hearing to all these things you have to reconstruct, right. So, some problems here are, so this if I am given the model, then this goes under the name of hidden Markov models, right, including there are 3 problems in that, prediction, filtering, smoothing and filtering, smoothing and maximum likelihood sequence, and if you have come across the Viterbi algorithm, that comes under the maximum likely sequence. Okay. So, these are goes under the name hidden Markov models. Again here you are just given this xi yi I equals, or here rather I should say that xt yt, because there is a temporal nature. So, some t equals 1 to capital T, and these under the, when the model is given, you the famous algorithm is something like Viterbi, right, and there is known as the forward and the backward algorithm. Okay. And this is where all your LSTMs, if it is data driven, it is LSTM, RNNs, transformers, right. Basically, if I take this data and then train a deep model, then these are the methods, corresponding methods. Okay. So, this is about prediction. So, now I am going to take down this side also. Okay. So, this is now again control. In control tasks, what happens is the following, right. So, there is this entire loop is full, right, it is complete. Unlike here, whatever you predict does not affect the environment. In a control task, whatever you decide actually affects the environment. Okay. So, I am just going to, yeah. Okay. So, then what is the very first part of this, basically static control. So, classical example of static control is this, you have this ad problem, Google ads problem, where you are shown the, I mean you have to show either ad in this location or this location or this location, and based on the way you show the ads, people are going to click and then they are going to get some reward, right. But the environment itself is based on your decision. If you place the ad here, you will have text in everywhere else. If you place the ad here, you will have text everywhere else, right. So, basically what you are deciding, your decision actually controls the environment. That is the difference between prescription and prediction, right. So, if I look at some doctor looks at an X-ray and then predicts, oh, the expectancy of the patient is going to be 10 years, right, that is a prediction. Then the doctor goes on to prescribe, saying that okay, you take these medicine and then your life expectancy is going to get better or your disease is going to change, right. Any action that changes, any task where you are controlling the environment, where your decision actually changes the state of the environment, that becomes a control task, right. So, this is single agent control, still only one agent, right. That was static control. This is so dynamic control is very straightforward. So, something like you are driving a car and then depending on your action set here is on the wheel and the clutch and the brake and the gear whatnot, and then based on whether you turn right or turn left, what you see ahead is going to change, right. So, whatever action that you will make changes the state of the environment, and the state evolves based on the way you act, then you get a corresponding reward, right. So, this is again control task, single agent, but dynamic. Okay. So, now here the so let us say this dynamic control task, you have to have, so it is basically a much more complicated data set, right. So, there is first a state, and then you look at an action, and then you get a reward which is a function of the state and the action, okay. And the next state depends on the current state and the current action, okay. And the model based approach is what is known as, goes under the word under the name Markov decision processes, and the ML method is what is known as reinforcement learning. Here you will have all your Q learning, actor critique methods. Okay. So, these are names which you have heard somewhere before, maybe otherwise you will hear in the future. Okay. So, here how does the data look like? The data actually becomes slightly more complicated. You have to say where I was, what I did, what I got, and where I went in next, right. The data itself is much more complicated now, right, because you have to tell all of these, right. Here no loop, no decision to be made, just the observations comma true label, right. And here also observations comma true label, but then you can take note of the fact that okay, the next label depends on the current label. Here the next state depends on the current state as well as the current action, that is where the control component comes, and the data itself is where I was, what I did, what I got as a reward, and then where I go next. Okay. So, now the next task is what is known as multiple agent decision making, which brings us to the game theoretic setting, where for example, a static thing. So, this becomes a matrix game, right. There is a row player and there is a column player, and then based on the row and the column play you get a reward, right, and people have studied what are known as repeated games in this setting, right. So, it is just a matrix game, you said repeatedly, and then you can think of all sorts of all the things that the vanilla notions that you had, right. Is there a dominant strategy, is there a mixers, you can always increase the number of players. I have just put 2 players, right. So, this is the static multi agent control. So, again you can have dynamic control multi agent, but that is again can be simultaneous. Okay, simultaneous, this is a very interesting problem that we are trying to sort of currently study. I mean, I am reading up on this with some of my students, which is this what is known as dogfight, where you have 2 fighter aircrafts and then they are chasing each other, right, that is known as dogfight, and you have deep reinforcement learning algorithms which are able to do that, but here the moves are simultaneous, right. I also move, the other person also moves, but then there are also setup where you have this alternative moves where you move and then you wait and then the next person moves. So, a very easier way to calculate, I mean capture the game theory also, the game theoretic control also in this setting is to say that you have to put another player, right. So, where I equals 1 to n players. Okay. If I add this, so basically this multi agent or basically multi agent control, these are what are known as competitive Markov decision processes. Right, and again this goes under the name multi agent RL. So, for a good book, this is you can look at Botseka's. Here there is a very good book by Filar and Rees, I think, Filar and Rees. Okay. So, okay, so this is the overall, I mean setup, just just this feedback loop. There is features, you make a decision and you observe the features, make a decision and receive a reward. You can pretty much capture all the interesting things that happen in AI, right, and almost all of these things you will come across in different courses. Okay. So, that was the very first part that I wanted to talk about, instead of thinking of all these things as somehow black magic or very disconnected topics. They are not so disconnected, they are all connected just with this simple diagram. Okay. So, yeah, so now what we will do is we will see why suddenly when all these things are happening, why is deep learning sort of in the heart of things, right, and why it is rightly so, or right. So, one of the important things in all these tasks is what is known as representation learning, right. So, as you are observing these features, see, either you are observing the state, as and when the agent receives the data, right, at this point, this is where the agent receives the input, right, any kind of input, here, any place, right. So, you have the option of massaging the data and then manipulating the input and transforming it into something else. So, here is a simple case where you have data in the form of this kind of Cartesian coordinate, where you have two clusters, two concentric circles, the red circle and the blue circle, but then somehow if you put it in, if you transform it to polar coordinates, you can sort of split the two, which means that if you have a mechanism to sort of change these features, right, then you can always use it for better description, better prediction or better prescription, anything, right, better control. So, somehow what happens is that the deep neural networks, right, because of all this, you have this architecture where you start with the data, do a sequence of linear, nonlinear operations, and somehow because you have this nested composition of nonlinear maps, you can sort of do this sophisticated feature transformation, and that helps in every task, because it does not matter whether you are doing unsupervised, supervised, reinforcement learning, game theory, any decision making. The moment you have the ability to transform the observations that you make into more useful form of representation, then you get a lot of power in decision making, right. So, because you, as we said, right, all of these systems you are not coding it as if then else statements, right, somehow you have to transform the data, right, and what is the right transformation to do with the data, that is what you are learning just from the data itself. That is why deep learning is powerful in all these decision making problems. It does not matter which problem you are there, you throw the deep neural network in. So, you always start with the deep neural network, as and when you get the data you pass it through a deep neural network, that is like a filter. Once data passes through this filter, it helps in any kind of decision. Okay. So, with this what I will do is maybe cover a bit of, I think I have to close by 3:30, maybe, yeah, it's okay, yeah, that is okay. Yeah. So, this is the overall landscape. Okay. So, now what I will do is I will look at, I will again we will be, I think, done by 3:30 at some, I mean that's let me try that, right. So, we will now look at alpha beta pruning, right, which was one of the classical methods that was in the 1990s, I believe. There was a match between Gary Kasparov and Deep Blue, right, and Deep Blue did this alpha beta pruning. So, this is an example of AI which has no machine learning. Okay. There is no machine learning and we will see why there is no machine learning. Okay. So, this requires the following setup. There is somebody called a max player, there is somebody called a min player, and there is a key component which is an evaluation heuristic. So, if I give you a board position, you should be able to somehow measure the material and position, mobility, whatnot, and come up with a score, right. And you sort of know why it is a max player, because whatever this max player tries to maximize, the other player tries to minimize the score, right. So, this was the setup, but then what people did was to use the setup to, I mean it is just a tree search algorithm, but then you can be intelligent if you have the right heuristics. Okay. So, what sort of evaluation heuristics you can use? So, you can always you can have the score, which is the difference between the white value and the black value, right, and how will you value? So, each pawn is worth 1, knight is worth 3, bishop is worth 3.5, rook is worth 5 and queen is worth 9. Okay. If I change any of these values, all the decisions are going to change, right. I mean if I flip these values, of course you will start saving the pawn and then you will start sacrificing the queen, right. And what is the white value? So it is the total of the white pieces, right, and the black value is the total of the black pieces, the weighted summation of the black pieces, and then that is the score, right. That is the score for the, that is the score which the white will try to maximize and the black will try to minimize. Okay. So, this was the setup, and with this let us see, I mean let us say just this. So, there is this game tree. Here I have taken a game tree which has just 2 actions, right, per node. Okay. First the max player plays, then the min player plays, then the max player plays. At each level you have only a branching factor of 2, you can have a much higher branching factor. Okay. So, what happens here is, okay, so what is the value? So, here the player will choose the maximum of these 2. So, okay, so this is the root, okay, this is the root of the tree. So, this is my current board position, right. From here I am thinking, what if I do A1, right, I am trying to mentally think, okay, if I do A1, then the min player gets the turn, the min player can do A3 or A4, then I get to move, then I can make A7 or A8. In this case I get 4, in this case I get 8, right. This is the set of all scenarios, states that are possible 2 moves ahead, right. So, this is just a 2 move look ahead, right, and here the value is very clear. So, I will choose the max player, if I am the max player I will choose the maximum of 4 and 8, and the maximum of 9 and 3 is 9, 2 and minus 2 is 2, and 10 and 11 should be 11 actually, sorry, yeah. So, this should be 11, and then the min player just takes the minimum of the 2, right, and what do I get in the end? 8, right. So, I will go with this. So, even though good rewards are available here, I obviously know that if I go here, the min player is going to drag me here, right. The min player will not give a easy move, right. So, I always assume that the other person is also rational and as intelligent. So, they are not going to give me an easy move. So, you do not take chance, you do not just hope that, oh, I will somehow reach this 10 or 11, you know that you are trying to factor in the, you are also trying to take account of the fact that the other player is equally intelligent.
So, is this a simplified version or is it what was actually used against Garrigues?
Yeah, this is the basic vanilla version, right. So, you will have to prove.
Score for positional.
Yeah, no, I am just making a, so they did some more, right. So, that is, this is the backbone, right, this is the backbone. The backbone is based on heuristics, right? This is just material heuristic, right. So, they also used a bit of maybe position also, but they also used some amount of what do you call, they stored lot of these chess books also. So, they also searched through some of the moves, past moves, so on and so forth. It is a mix of things, but the key heuristic is this search. Okay. And again, yeah, sure.
At the leaf node, what's deciding the value that the
Yeah, so there will be some evaluation. Suppose I give you 2 minutes. See, suppose I give you on the clock just 2 minutes, right. So, maybe you have only time to expand to level 2, and then all that you say that, oh, I will have 2 pawns, the in this position they are going to have 5. So, what blah blah blah, and then I know this is the position, this is the position. So, I can evaluate, these are all evaluations, right. All the square ones are evaluation, some heuristic evaluation, right. Yeah, that is what I told. Yeah, it should be 11. It should be 11. Yeah. Okay. So, now this is the min max algorithm. So, all that you do is, so the max player starts with a board position, and for all the actions in the action set in that state, you look at the next board position for all those actions. Then what you want to do is you have to give it to the min player, right. So, then what does the min player do? I mean, if the depth, right. So, I want to expand till some depth. If the current depth is greater than the depth, you just evaluate and then return the position. If it is going to be terminal, right. So, maybe the game actually ends, then you say that you terminate and then you give the position. Otherwise, what you do is you again recurse, right. You again expand on all the actions and give it to the max player, right. And the min player takes the minimum of all the options, all the values, and when you give it to the max player, again the max player takes a maximum of all the values, right. So, the min eval calls the max eval, right, which is basically from this level you will call this guy calls this calls this, right, and yeah, that is it. So, this is just the min max algorithm, this is the vanilla algorithm, right. So, you have not yet done the pruning. Okay. So, again let us see how this tree gets built. So, okay, first you will expand the first one and then you will start recursing. So, you will call this loop, okay, then the min player will again play its first action, then again call the max player will play its first action, then first it will get its evaluation, then its next action, then its evaluation, then the min player plays its second action, and so on and so forth, right. So, this is how it happens, and then eventually you get this thing populated, right. So, the neat thing that they did was to do what is known as alpha beta pruning, which is to say that, okay, suppose I have done some evaluation, okay, somehow I evaluated this branch, right, maybe I am evaluating for depth 10, right, I evaluated this branch, I know that I am getting 5 here, okay, in this branch I am getting 5. So, I go into this loop and suppose the min player is getting 3 here, let us say, right. So, I will never, I do not have to look for these options, I do not have to expand this part of the tree. Why? Anyway I am getting 5 here, the moment I make the first move here, the opponent can drag me to 3, that is actually bad, right. Then why do I have to see, he can drag, right, they can only drag me even lower, right, there is no point in actually evaluating this part of the tree, you can just cut it off. So, this is the intelligent part, right. So, you do the pruning, so this is known as alpha pruning. The same thing you can do for the min player, where the min player, suppose the min player is already getting 6 here, okay, and it wants to, it is again looping, recursing, and then asking what the max player makes, and say suppose the max player makes 7, then the min player does not want this, because the moment the min player has a better move here, why will I even do this, and then why do I have to evaluate this branch. So, this way what you can do is quickly, so even though let us say 10 depth and then at each level you have 10 moves, it is actually 10 power 10 leaf nodes, right, you do not have to actually visit all the 10 power 10, the minimax algorithm would have, this does not, because you are quickly throwing away things. And it so happens that in a game like chess, many of the practical states you can sort of prune this thing, right, and it is some kind of a anytime algorithm, meaning say suppose I give you 3 minutes or what not, right, I would have done some evaluation and then finally I will just come up with the best move that I have evaluated till now, right, I do not have to fully expand the tree, fully prune anything, right, and then you support it with other heuristics, right, other chess games and so on and so forth, but then this is the backbone. Okay. So, why was this was exciting, because okay, with this they were able to beat Garry Kasparov, but the sad part or the letdown is that you need this heuristics, right. Where is the heuristic is coming? The heuristic value is just by human experience, right. Somehow we have played lot of games and then we are saying that, oh, queen is worth 9, if queen was actually worth, if you change the worth of the queen to be 7, then all the things are going to change, right. The entire AI's capability is going to be very different. So, it is extremely sensitive on the heuristic values, and there is no learning here, no learning, just pruning, okay. There is no learning. Okay. So, again, so this is alpha beta pruning in full detail. All that you do is you sort of keep passing these values.
So can I ask?
Yeah.
With this sort of pruning, it's a lot like what we do in a bounded search tree type thing. Below certain configurations are not worth going down.
Yeah.
Because that's the thing, right?
Yeah, that's
it's very much like a standard algorithm. Where
yeah.
some recursive steps sort of thing.
Yeah, you can just eliminate some of them. Yeah, that's what it is. And this is just the minimax algorithm, will just the cutoff conditions. Everywhere you maintain the cutoff and then you cut off the tree. Okay. So, the reason why this is not okay with game like Go is the following. So, there is no direct way of measuring the who is the quality of a board, right, because it is with very sophisticated rules of how much area was captured, so on and so forth. But then what you can do is you can say whether victory or a defeat, that can be only that feedback can be known, it is only 0 or 1 feedback, you do not have any way of intermediate evaluations. there are no heuristics, you cannot say that this has a heuristic, this is as, I mean these are like 19 cross 19 and then each thing can be 3 combinations. So, it is like 3 to the power 19 square, right. That number actually exceeds the number of atoms in the universe. Okay. So, this is what this is where people were stuck, right, which is why a lot of technology has to catch up in terms of technology, in the sense that yeah, of course, you needed the GPU machines, you needed a lot of research in reinforcement learning algorithms, deep learning, and all of these things had to come together to build what is known as AlphaGo, right. But the idea behind AlphaGo is sort of Monte Carlo tree search, upper confidence trees, and RL, right. Let me just quickly go through, I mean before we go through upper confidence trees.
What's the use of RL here?
Yeah, we will come there, right. So, what you do is as somebody was asking how do you play, right. So, you do not play against human beings. What you do is you have a randomized agent, you have an agent, you have 2 learning agents which learn by self play, right. Once I learn by self play, right. So, both agents are sort of playing some randomized strategy. These randomized strategies are getting intelligent as they train, but they are kind of trying out various options and learning. Okay. So, now what happens is that once it gets randomized, you can just sort of forget the other player, right. You do not do this strategical thing of I think, they think, that I think, that they think. You just say that okay, there is one environment, everything is an environment, I make a move, then something random somebody else does, and then I see the next board position, right. So, you sort of abstract out the other person, the other player is also symmetric, right. So, then it becomes a standard reinforcement learning setup, right, where we will now sort of quickly go through a very simple RL problem, right, and then we will understand how things like what are known as states, actions, rewards, policy, so on and so forth. So, this is a very simple problem. So, there are some 9 states, okay, and but for every other state other than the top right corner, everywhere else you get 0 reward. Then you have actions which is either go right, go left, go up, down, or this is just stay, okay. And your objective is you want to somehow maximize the discounted reward, right. So, you can keep moving around this sort of maze and in this grid, and your aim is to sort of maximize this, right. I have taken out the randomization and all that. So, all that we can put it back in. So, to keep things simple. So, what would you want? So, what will be the, so for example, I have a policy, I can start with some policy which says that I will just stay everywhere, right, wherever I am I will just stay there, I will not move anywhere else, right. In that case, so suppose this value of gamma was say 0.9, then here I will get value to be 10, right, 1 plus 0.9 plus 0.9 square plus blah blah blah. So, that will be 1 by 1 minus gamma, and for the value of gamma equals 0.9, that will be 1 by 1 by 0.1, which is 10. So, here only I get a value of 10, right. This is what is known as a state value function, right, and this can be obtained by solving the simple equation. All that it says is that oh, I get in this state this much, and in this policy if I make an action according to this policy, then I go to some other state, from there I get so on and so forth. So, this is the state value. This is quite simple. So, all that you want to do is, so this V pi of s, this is the current state, this is the current reward, this is the result, right. This is the immediate future. Right. This is the current value. So, the current value is basically the value in the current step, and then what you will collect in the immediate future, right. So, once you solve for this, you can solve for the value function, but that is not the, that is just one part of it. The most interesting part is what is known as the q value function, which tells you what is the difference, what is the, what do you call, something like a marginal contribution, or what is the contribution of each effect of each particular action in a state, right. It tells me that okay, if I do a particular action now and then follow the policy, what happens, right. So, for instance, if I am at S8, right, and I decide to go right, okay, so I get 0 now, then for gamma equals 0.9, from tomorrow onwards I get 10, so I get a total value of 9, right. This is with respect to stay everywhere policy, right. This is my policy, stay, 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 stay. Now I want to say that okay, if I want to deviate, which direction should I deviate, right, in each step. So, should I stay here or should I go here or go down, that is what I am trying to evaluate with the q values. So, if I try to say that oh, what happens if I go left, then I will go to S7, but then I get 0, right. If I go down I get 0, if I stay also I get 0. So, that means somehow these state action values tell you in every state which action is better, right. So, you calculate this state action values, okay. So, for instance, in state 1, I mean every value is, every action is kind of, there is no discrimination, right, everything is giving you a 0. So, what happens is that you can sort of do what is known as policy improvement. Your initial policy was to stay, stay, stay. This is imagine that the initial policy is the current way in which you are playing, right. The agent is trying to play in one way, and then the agent wants to know how to improve, right. It can improve if it knows the q values, the state action values, which is basically in this state, which is S8 and S6, you can sort of improve. You can understand that moving right is beneficial here and moving up is beneficial here, right. Whereas, in state 1 you will just say that okay, I will stay, right. You can do anything, but then you will not learn, right. But what happens is that slowly you can do this loop of policy evaluation and policy improvement. You can evaluate a policy, you can just play around, right. But then as you play around, if you know in each of the states which action is more sensitive, right, which action is more rewarding, and then slowly shift your decisions to favor that action, right, you can improve the policy, right. So, what you do this is this loop of policy evaluation and then policy improvement, okay. So, now this if you do it with respect to a game tree, then that becomes what is known as the upper confidence trees, okay. So, now we can go from the deterministic world to the random world. So, in a deterministic world, what you do is that there is a state node, then you have state action nodes. So, this is how you change the modified game tree, because the other player does not exist, all that exists is your state, and then you maintain state action nodes to understand which action is more rewarding, okay. So, in a deterministic case, all that you need to know is that okay, each of these actions gives a result, right, of some other state, and then from the next time instant onwards you see the future, okay. This is again just the one step, I mean current reward plus the future reward, okay. And if you just have randomness, all that you have to do is, if the states are random, if the transitions are random, for every action if you go over a spread of these states, you just add the probabilities, you just put in the probabilities and then just average it, right. And if you are taking random actions, then again average over the randomness in the actions, right. This is just basically the same equation. If you have randomness here, if the resulting state for a particular state action pair is random, then so there is randomness in the next state, so you average out that, and if the actions themselves are random, you average over that, right. But it is just simple equation which is current reward plus what I get from tomorrow onwards, that is all it is, okay. So, now this is the modified game tree, right, one particular node, state node and the state action node.
Can I answer?
Yeah, sure.
This sort of a transition, it's very Markov-heavy. I would be dependent on my current
Correct.
ranking on the history.
Yeah, to some degree it's true, right, like it does not matter how I got to a particular board position, right. Once I am in the board position, I am there, right.
In Go it matters, right, like how much area I have covered and all.
Yeah, but given a position, that is how it is, right. It does not matter how I reach that position.
Given the position, everything is fixed.
Yeah, the past does not matter. given the position. It's almost same in every almost lot of RL cases, right? I'm doing automatic driving, right? Doesn't matter where I reached here, wherever I am, the future depends on the current state and the actions. Right?
But could it be that, like, say in a strategy, I know that someone has played this two these steps and then this one, so it's most likely that he will now play this.
So those are all. So you are sort of, that's where you are assuming the rationality, right? So you are sort of thinking that the other player will be as, but in this case we are not even banking on that. We are thinking that both of them are random players, right? And then they are learning from each other. Okay. So maybe I think there is not much of adversarial nature. So what happens is that both of them are similar players. They sort of improve
both of them
learning together, right? So yeah, so what happens is you just do this upper confidence trees. What you do is you maintain the Q value for each state, which is nothing but the number of wins you obtain through any node, right? So you, in your tree, you maintain number of times you visited a state node, and separately the number of times you visited a state action node, and in each state node you play this bandit, right, which is the upper confidence bound. You would have looked at multi-arm bandits in the upper confidence bound algorithm. All that you do is you maintain the Q values, but at the same time you have this exploration bonus or whatnot, the confidence interval, which tells you, okay, some of the actions if I have not tried, I will try, but then at the same time I will favor the ones which are more rewarding. Here the reward is the number of wins through that particular state action node. So all that you do is you do what is known as Monte Carlo tree search, but then in the tree search, so there are 4 steps, right. The first step is what is known as selection. So you maintain a game tree, right, and then you select, right, you select based on which is the best upper confidence bound value, then you sort of expand, and then what you do is you play random games, right. After that you do not strategize, this is just a random trial, you just play random, both play agents are random, they just play, right, and they go to the end. In the end, you know, somebody would have won, somebody would have lost, or it is a draw, right. That is your signal. With that what you do is you populate, right, and then you back propagate, you basically maintain the number of wins attained from each state node and state action node, right, and that is what it is. So you maintain this upper confidence tree where you have state nodes, state action nodes, again state node, state action node, so on and so forth, and each of the state nodes you store the state value, each of the state nodes, state action nodes you store the Q values, but then in each of the state nodes you play the upper confidence bound algorithm, and after a particular depth you just do random self play, right. So this is basically upper confidence trees is nothing but Monte Carlo tree search which people were doing long time back, but then once they understood that you put this upper confidence bound algorithm to select the nodes, right, it becomes much efficient, because previously what they were doing is uniformly they were exploring all the options. If you are going to uniformly explore all the options, you will pay as much as the breadth here, right, but if you are going to do the upper confidence bound strategy, most likely you will be only playing the promising moves at everything. So even though you will explore everything, you will be actually only exploring and deepening the tree in the line which is more promising, okay. So now all you have to do is to sort of combine it with deep learning, right. So what you do is, okay, this is both players are playing against each other and they are actually building this tree, right. Now how do they remember? So the moves that they remembered, right, so that is encoded in a deep neural network. So you use a deep neural network, again you give this as the board position as features, the neural network spits out 2 quantities, one is the probability of choosing particular action in a state and the value of the state itself, it predicts these 2, right, and you sort of play your upper confidence value, you derive it by the Q value, but also this confidence bound which is proportional to the probability that you have to pick that action divided by the number of times, right. If you pick a move a large number of times, then this denominator will dominate and then you will stop exploring. If you have not touched a move for a long time, then this denominator will be less and then you will explore that move, okay. So you use the deep neural network to give you these surrogate values, to build the tree, and then using that you find the promising move, right. Then what you do is you continue to play till the end, right. Once you play till the end, both of them are random agents. So, you will know that in the end somebody won or lost, then you propagate, right. Then you train the neural network to exactly estimate the value of each of the nodes, okay. And you also train the neural network to sort of match these probabilities, right, the probability of playing, right. So, that is the policy, right. So, the UCB policy, right. So, it is using the upper confidence bound values, right, to play these explore the tree. So, you see how it explored at the root, right, and that is the policy that it followed at the root, right, and then you sort of train the neural network to predict this. See, this is where what happens is that you have something very principled first in the name of upper confidence bound from tail bound, so on and so forth. You derive the UCB algorithm, then you do something, and then when you lift it up to the deep learning space, you sort of do lot of hand waving, and then you hope that the heuristic works, right. At this level it is just a I mean this is all hack, because no one knows what is being what is learnt internally in a deep neural network, but the hack is basically principled on upper confidence bound algorithm, right. So, it is basically upper confidence trees, which is nothing but Monte Carlo tree search plus UCB. Now, you put in this deep neural network, and then you do millions and millions of games, and that is how we were able to achieve whatever we were able to achieve in AlphaGo and chess. Okay, so, with this let me conclude. Okay, so, what we did was to look at this decision theoretic framework for AI, then we looked at alpha beta pruning, which is a very no data driven method. Then we looked at upper confidence trees, which is basically RL, but it is based on the upper confidence bound algorithm, which is a bandit algorithm. Then you take that and then sort of combine it with deep learning, where you also take the support of the deep neural network to guess the play of the probability to choose the action, and also the estimate of the values, right, and all these things together. Now, this is like this is a technology, right. I mean, at some point this was math, till this it was just math, till just UCB it is just pure math derivation, you can just prove things and other stuff. After this becomes just technology, right. It is like pour more oil, pour more whatever, and then you press the pedal and then it goes faster, right. It is just fueled, right. This is all just more and more fuel, okay. But then that is where engineering comes. You understand the math very clearly under very controlled conditions, and you understand the bounds, then you will be able to engineer these things better here. But what this is just engineering with lot of hand wavy things, and of course, thousands of hyper parameters would have gone, and then hundreds of engineers tuning all these architectures and so on and so forth. Otherwise, I mean nothing just comes that way, but the principle is just I mean until this much it is just principal mathematics, after this is just engineering. Okay. So, maybe with this let me just stop, and yeah, there are any questions, maybe we can